Welcome back. I want to continue the discussion of the cohomology of Eilenberg-MacLane spaces. And our goal, sort of a short-term goal, is to use the Serre spectral sequence to compute the cohomology of kz mod 2 n, our Eilenberg-MacLane space, in mod 2 coefficients. And I've already given you this as an exercise, so you might wonder why bother, but we want to compute this not just as a ring, but as a module over the Steenrod algebra. So this is an unstable module. Okay, and in this video, our aim will be to prove the following theorem, which is that there's a map from the Steenrod algebra to, I'm going to call this n plus star. So the Steenrod algebra is graded, and of course the cohomology is graded, but I want that grading to start at degree n. Let me finish what I'm writing and explain what I mean in a moment. So this will be the cohomology of our Eilenberg-MacLane space, of course. And what is this map? Well, the map is easy to define. We should just take square I, and where I is some sequence in the squares, and then we should send it to square I applied to that fundamental class, iota n, which lives in degree n. Remember, coming from the inverse Hurewicz isomorphism at that degree. So notice this is not a map of degree 0 of these graded rings. This is, or modules, or whatever, algebras. This is going to be a map of degree n, right? So square 0 is going to go to square 0 iota n, which lives in degree n. So, okay, that's what I meant about this degree shifting stuff. And what is the theorem? Well, the theorem is that this is an isomorphism for degrees less than 2n. Okay, so what I think of that as saying is that the cohomology of the Eilenberg-MacLane space looks like the Steenrod algebra for a while. Well, really this kz mod 2n, our Eilenberg-MacLane space is n-1 connected. So there's nothing interesting up until we get to degree n, and that first interesting thing is this fundamental class, iota n. And then from degree n up to 2n, we're seeing something that looks like the Steenrod algebra. Okay, so we'll see more and more of the Steenrod algebra if n is larger. And so we have this immediate corollary. I guess almost immediate. Maybe you have to say something about this inverse limit, but this inverse limit turns out to be nice. Ooh. And what inverse limit am I talking about? When we take the inverse limit of the cohomologies of our Eilenberg-MacLane spaces, we're just going to see more and more Steenrod algebra. And so, indeed, that's how we get this corollary that this is the Steenrod algebra. And so what was that all about? Well, we saw in the last video that the Steenrod algebra then classifies stable cohomology operations, because those stable cohomology operations, cohomology operations corresponded to maps between our Eilenberg-MacLane spaces, and the stable ones we wanted to commute with suspension, and so we took this inverse limit. Okay, great. So this is the theorem that I want to prove, that we can compute the cohomology of these Eilenberg-MacLane spaces, and at least up to degree 2n, it looks like the Steenrod algebra, so Steenrod algebra for a while. How will we do that? Well, finally we get back to spectral sequences. So let's go back to the Serre spectral sequence. And do this computation. Okay, so remember, of course, our Serre spectral sequence has a nice E2 page, and it's the cohomology of the base with coefficients in the cohomology of the fiber, converging to the cohomology of the total space when we have a fibration from E to B with fiber F, and I guess we want pi 1F acts trivially so that we don't have to worry about local coefficients. And then we'll need a definition. So there's a special differential called tau. This is going to be dn from en 0 and minus 1, so on the nth page, to, well, we can just calculate the degrees. That's going to have to go to en n comma 0. And this tau has a special name. This particular differential is called the transgression. And this has already come up for us some in discussion, so I imagine this is familiar to some of you. Just a little bit more terminology. So if I have some class and di on it is 0 for I less than n, so that it lives to the nth page, but then dn of x is this particular dn, so in this particular degree, so it turns out to be tau of x. If we then get something non-zero, then we call our x transgressive. We might say it supports a transgression. Okay, so remember that our Serre spectral sequence is a first quadrant spectral sequence. So let's look at our EN page. So we usually draw P and Q here. So on the EN page, we're talking about looking right here on the Q axis at something in where Q is equal to n minus 1. And maybe there's some little x there. And mapping over to the p-axis at degree n, and that's our transgression tau. So it's almost, maybe I should have reminded you that our dr differentials have degree r comma minus r plus 1, right? So we're in the cohomological spectral sequence. They go to the right and down, and really this is just sort of a technical way of saying, yes, this should go from the edge to the edge. So from the q-axis to the p-axis, that's the transgression. Now, of course, there are other dn's on this page, potentially, but those are not called the transgression. It's only when you go from the q-axis to the p-axis. So it's a special dn. And really, we were just lazy when we even called that dn. We maybe should have called it dn 0, comma n minus 1 to be really precise, right? Okay, so that's our transgression tau. And why does this matter? Well, let's tie this back into the Steenrod algebra. It's a fact that if x is transgressive, so tau on x is defined and is non-zero, then you also know that square I on x is transgressive. Okay, so square I on x is going to take you somewhere up the q-axis because it's going to be something in the cohomology of the fiber. And then if x supports a transgression, then you know that something over here gets hit by that thing on the q-axis. Okay, so that's, notice, going to happen on a different page. And we can even make that a little bit more precise. So it's even better than that. So there's square I of the element that we hit is the transgression applied to square I. So I say the squares commute with the transgression. Okay, maybe let me write that. That's really the slogan that I want to remember. Okay, so the squares commute with the transgression, but notice that here the transgression might be dn, but here the transgression is dn plus I, because square I of x is going to land in degree n plus I, and so in order, oh, maybe it's even, I think I might be off by 1. Let me think. No, I think that's okay. Well, not a big deal if I'm off by 1, but I think that's okay. So in any case, this cohomology operation is going to take me up degree I, and so I will need a longer differential to go from edge to edge. So the transgression will be on another page. Okay, I'm not going to prove this, but let me say that the important part is that this really follows from naturality. And I think you could take that and come up with sort of a nice, sweet proof if you had enough sort of structure behind you. But this is from naturality of the square I's. But the way that it's usually proved requires quite a bit of chasing. I'll call it some chasing through the diagrams in the construction of the Serre spectral sequence. And we've talked about that a little bit, so that might be a nice thing to do. Most people tend to refer you back to Serre's thesis, where this is proved. And remember, Serre's thesis, I think, is actually quite nicely written, but it is written in French, so it can be a little bit of a challenge. I think you can also find a description maybe in Hatcher or Davis and Kirk, so if you're interested in chasing this down, I encourage you to. Okay, so what are we going to do here then? I guess I'm going to run out of room on that page, so maybe let me put it here. The claim we're making is that if we wanted to look at the cohomology of some Eilenberg-MacLane space, kz mod 2n, in mod 2 coefficients, that we actually have a pretty good sense of what it looks like. So let's do reduced, why not? So this should be 0 in degree 0, since now we're doing reduced. And I should have a bunch of zeros up until that fundamental class in degree n. Okay, and then what I'm supposed to see is the Steenrod algebra. So I should have square 1 iota n in degree n plus 1. I should have a square 2 iota n in degree n plus 2, and so on. I should have a square 1 comma 2. Okay, so now I'm using that sequence notation, that's square 1 after square 2, and remember that's not the same as square 2 after square 1, so that's another thing there, and so on. And I should see basically the Steenrod algebra begin. And then when I get up to degree 2n, well, some other stuff. Okay, so we're only making this claim in our range. And I think it's kind of nice to draw the picture here. So in degree n, I have iota n, and I don't have anything interesting before that. These are all z mod 2's, and so I tend to just draw dots for z mod 2's. And I think you've seen this already in some of my pictures. In degree n plus 1, I should have square 1 on that class. I should have a square 2 on that class. I should have square 1, square 2. I guess it's going to land me up here, and so on. Okay, so let me leave it as an exercise to draw the beginning of that free module over the Steenrod algebra. But of course, this won't be free forever, so at degree 2n, something else happens. And we'll say more precisely what later on. But this is what we want to prove. And then, of course, we can just take the map from the Steenrod algebra to this by sending the squares to the squares on this fundamental class. Okay, so how does the proof go? Well, I'll basically give you a sketch here. So what we're going to do is induct on n. And of course, we know the cohomology of kz mod 2, 1 in mod 2 coefficients. That's just Rp infinity. And we know as a ring, that's just polynomial in a class X. And we've also talked about drawing what module we get as a module over the Steenrod algebra. So maybe let me make that 1. Here's X, and that's iota 1. Okay, I know I was kind of sloppy earlier and said we'll talk about fundamental classes for higher degrees, but this one works out just fine. Then I've got x squared, or iota 1 squared, and so on. X cubed, x to the 4th. Let me not draw too much here, but remember that square 1 squares x, because x is in degree 1, so we get x squared, and square 1 on x cubed was x to the 4th, and we didn't have a square 2 on x. Remember, this is a module, an unstable module over Steenrod algebra. Square 2 is in degree 2, which is bigger than degree 1, so square 2 is 0 here. But square 2 on x squared, well, now we're in the good degree for squaring. So we had that connection, and so on. Okay, so let me just stop there. But, okay, the point is, if we want to look at degrees less than 2n, and our n is 1, then we're really only looking here in degree 1, and yeah, okay, there's not much to say there. Our base case is really trivial. But notice that this does become much more complicated. Maybe more complicated is a weird word at the moment, but what I mean is it doesn't look like the Steenrod algebra at the bottom. I see Steenrod squares acting, but it doesn't look like it's starting out with this picture, right? Okay. Great. So our base case is really trivial for degree reasons, but yes, we could start there. For the inductive step, really the interesting part, what will we do? Well, we want to use the Serre spectral sequence, and we'll compute the cohomology of kz mod 2n, of course in mod 2 coefficients, via the loop path vibration. So we'll say inductively, we know this for kz mod 2n minus 1, and then there's paths on kz mod 2n, and really that kz mod 2n minus 1 was just loops on that. Okay, so what does that look like? Well, I want to draw my Serre spectral sequence. I'm going to put the cohomology of the base down here on the p-axis. I suppose that's the thing that I'm after, so maybe I should hold off, but that's going to be the cohomology of kz mod 2n in mod 2 coefficients. Okay, and then up here I'll have the cohomology of the fiber. So that's the thing I'm assuming that I know. Kz mod 2 comma n minus 1 in mod 2 coefficients. Getting crowded here. Okay, this is going to take up a lot of space, so let me give myself a pretty big grid here. So this is all going to be p equals 0. And then here this will all be q equals 0. And of course, if I am working reduced, then I just have 0 at the bottom. I want to have my ring structure, so I've written this as unreduced. Doesn't really matter. But of course I have 0 all the way up until that interesting class, that fundamental class. Maybe let me scooch it down a bit. That fundamental class iota n minus 1 in degree n minus 1. Okay, and then because I have all of these zeros, and because I know that kz mod 2n is n connected, or sorry, n minus 1 connected, then I know there's nowhere for for this class to die until maybe it gets to, let me scooch that, until maybe it comes and hits iota n. Okay, so there's my transgression tau because it's going from the q axis to the p axis, right? But now this fact about the squares commuting with the transgression tells me, well, I know that this thing on the left here looks like the Steenrod algebra for a while. So I've got my square 1, and I've got square 2, and I've got square 2 square 1. I guess that should go up a little bit higher, and so on, right? So I've got my little Steenrod algebra here. Maybe let's put in square 1, square 2. Okay, where was I going with that? So I've got square 1 on this iota n minus 1, and that must transgress to square 1 on iota n. Similarly, square 2 on iota n minus 1 must transgress to square 2 on iota n minus, sorry, let me say it again, I'm struggling here. Okay, in minus 1 comes and hits iota n. I don't know why I'm saying I. Okay, so square 1 commutes with a transgression. It must come and hit square 1. Maybe let's even put that differential. Okay, so now this is a dn minus 1 differential, but we'll still call it tau. Square 2 on it has to, oops, supposed to be hitting that. Square 2 on this has to come and transgress to square 2. And so I've got a square 2. And I've got square 2 on this, and square 1, and so on. And so I get that same picture turned on its side. Okay, so why doesn't this just go on forever? It seems like I'm getting a free module of the Steenrod algebra generated on iota n. And the reason that I don't is, remember that we have this nice tensor product structure here, say on the E2 page. So on the E2 page, since iota n and iota n minus 1 live on the E2 page, it makes sense to talk about iota n minus 1 tensor iota n. I'll just write times. Okay, so I've got this tensor product here, but now I also can use my Leibniz rule to see that the differential on that has to come and hit, maybe let me do this in a different color. So this has to come and hit iota n squared, right? Just use that Leibniz rule, okay? And this is the same game that you played when you were computing the ring structure, of course. You would use these tensor products and see, okay, that fills in a lot of differentials. But now what that tells me is that something else starts to happen in degree 2n, right? This is in degree 2n over here. And so I really only know well what's happening up through there. We'll ultimately come back and compute the entire thing using work of Borel and Serre. But as of right now, we see that, yes, okay, we definitely have this Steenrod algebra for a while. I guess you could argue that square n on iota n is iota n squared, so that still looks like Steenrod algebra stuff, but if I keep going, then I should see some maybe more complicated stuff up here. And so let's just say for now, we don't know. But at the very least, we certainly have Steenrod algebra for a little while, okay? And now taking the inverse limit of these, our Steenrod algebra grows and grows and grows. And indeed, that Steenrod algebra does classify our stable cohomology operations. Okay. So you might find this a little unsatisfying at the moment. We didn't do the complete calculation. We'll come back and do that in the next video and continue on our way. But remember that ultimately all of this work is trying to build up to computing the stable homotopy groups of spheres. So we'll sort of leverage this computation and this Steenrod algebra to get that started using the Serre spectral sequence. All right, let me stop there for now.